Okay, we have in number 9 we have x squared plus y squared equals 169, and it tells us that we want to find the equation for the line tangent to this curve at the point 5, negative 12. So ultimately we should recognize this as an implicit differentiation problem, because we don't have an equation that's solved for y. So if we want to write the equation either way, we're going to wind up with y plus 12 equals m times x minus 5. That's going to be 2 out of the 3 things that we already know because they gave us the point in question. So from there we need to come up with the slope. So if we differentiate here with respect to x, we get the following. And then from there, if we subtract and divide, we're going to get y dy dx over here, and this is going to end up with negative x over here. So we're going to subtract 2x and then divide by 2, and we could also divide by y, and we'd wind up with dy dx equals negative x over y. So if we implicitly differentiate that, solve for dy dx, then we can find our derivative. And again, at this point, we're going to find the slope. So put in negative 5 over negative 12 would be 5/12. So negative here because 5 was positive, so negative 5, plug in a negative 12, positive 5/12 will be our slope. So with that said, we have y plus 12 equals 5/12, x minus 5. And if you look at the choices, is that one of the choices? No, all the choices are in standard form, it looks like, so we both ultimately need to do that. The other thing that the choices don't have is any fractions. So remember our clearing fractions technique, we can multiply everything by 12 first. So I would clear the fractions.
When you plugged in the 5 and the 12, why do you have negative 5 up on the top?
Because this is a negative x. So we subtracted that to the other side, so it was a negative x on the right. So it would be negative x over y as the derivative. And then from there, once we clear that fraction out of there, we can distribute here. And if we get everything on the same side, we'd have negative 5x plus 12y over here, and we'd have negative 169 here. And now looking at that, is that an option? Is it an option? No. Okay. So ultimately, how can we get it to be an option? If we were to multiply the equation by negative 1, which is okay because of the multiplication property of equality, it's okay to multiply the whole equation by a number, and we'd get an equivalent equation if we did that. We could make it so our coefficient on 5 would be positive. Now, is that an option? Looks like letter C. So ultimately, in the scheme of things, this is a calculus problem, right? Okay. What else did they figure out whether you could do or not on this problem? Yeah, you got to do a fair amount of algebra to come up with the right solution, didn't you? Okay. So are there algebra problems on the AP test? There's not really problems that are just strictly algebra problems, but ultimately are they going to be able to test your algebra by doing something like that? Absolutely. Okay. Other questions on number 9? What else? Through 14. Too easy. That's good. Oh, okay. Not so much. 13 says we have a graph f of x, 2x squared plus k over x. And it says that this graph has an inflection point at x equals 1, or negative 1, and we want to find the value of k. So ultimately, what do we know about inflection points? Where do they occur? The second derivative equals 0. So if we find the first derivative here, we'd have 4x. And then if we have k over x, remember we can rewrite that as kx to the negative 1. So ultimately the derivative of that would be negative kx to the negative 2. It would be minus k over x squared. Alright, so with that being our first derivative, our second derivative, of course, is going to be 4 minus, and if we do the same thing here, if we let that be negative k to the negative kx to the negative 2, we'd have positive kx to the negative 3, so it would be plus k over x cubed. So we find our second derivative, and we also know here that the second derivative equals what? It equals 0 at what? At x equals -1. So ultimately, wouldn't our equation look like that then? 4 plus k over -1 cubed equals 0. They told us that, and we know that there's an inflection point, then the second derivative has to equal 0 at that particular point. And what's the point in question? -1. So ultimately, we'd have 4 minus k, or 4 that is, 4 minus k equals 0. So negative k would equal -4, k would equal 4. Questions on that one? Oh, really? Let's see. Did we miss something then? Where did we miss? This is for... Oh, I know what I missed. There's a 2 right here. Sorry. There's a 2 here, which means there's a 2 here, 2 here, 2 here. So k would be 2. Our second derivative would be not... we'd have to have -2 out in front. Positive 2, it turns out, because it's minus times minus. So k equals 2, that should match up with letter E, is that what I said? Good. So again, when we do that second derivative, it's negative kx to the -2. So ultimately it would be positive 2kx to the -3. That's why there's a 2k on top. Alright, what else? On 12, we have an integral problem where we have 4 minus x squared dx. And this is one where we got to do a little bit of thinking. If you look at it, it's not a known derivative, but it's kind of close to a known derivative. And what function do we know has something very similar to that as its derivative? Sine inverse. Okay. So it looks like sine inverse, but the problem is the sine inverse needs to be of the form, and if you need to go ahead and write it down. You got sine of u, the derivative of that would be 1 over square root of 1 minus u squared times du dx if we use the chain rule part. Okay. That's our definition of derivative of sine u. And so if we can recognize it as something like that, then maybe we can write it as that exact form. So we ultimately need to have 1 minus u squared under our radical in order to have this work. Okay? So what it's going to take then is to get that 4 to become a 1. Fair enough? So the question is, how in the world do we do that? Well, just like this. If we were to go under the radical and factor a 4 out of that expression, we would have 1 here, and then we'd have x squared minus 4 here, wouldn't we? True? Okay. That would still be the same thing. I could multiply back in, I'd get right back to what I started with. Agreed? Mm-hmm. Alright, and then ultimately, since it's a multiplication now, where can this 4 go? Yeah, out. Okay, in fact, it can go all the way out. And now my sentence would read this. Now watch this, one more step in here. Instead of writing x squared minus 4, I'm going to write this as x over 2 all squared. Okay. Because ultimately, isn't x squared over 4 the same as x over 2 all squared? And now, what form is it in now? Doesn't it look like 1 over square root of 1 minus u squared? Okay. Now, after tomorrow, we'll have a little bit better basis for finishing the problem here at this point. I'm going to finish it for you now anyways, give you a little bit of a preview of what we're going to do for tomorrow. Okay. Is ultimately, if this is some expression other than x here, if this was just an x, our answer would simply be sine inverse x plus c. True? But since it's not just x, okay, then somehow there's a chain rule issue here, and we know how to deal with that with sine and cosine because we have some rules there that we developed. But the question is, how do we deal with that with just some general function if we have some argument there that's not just x? Okay? And again, I'm going to show you this now, and we're going to do more of this tomorrow in the next couple days. But ultimately, what we do is we write it in terms of u, because we want it to look like this when we get done. True? If it looked like that, we'd be good to go. It'd just be sine inverse of u. True? So what we want you to do is get it to look exactly like that. So we can do that by doing what we call u substitution here. We can substitute the x minus 2 because that's the issue. True? But what we're going to do with that then is from here, when we do the substitution, we're still going to have a half out here. We're going to have this, 1 minus u squared. We're good to go there. But the problem is we can't stick a dx here now because the u and the dx aren't the same variable. True? So somehow the dx has to be gone too. Now, here's the relationship that we're going to look at here then, is what's the relationship then between dx and du? Because ultimately we want, if this variable is going to be u, then we need to have du here, not dx. True? So what would du be here? Well, if u is this, then du would be 1/2 dx. Agreed? So that means that right now, the only thing that's holding me back is I got this dx here. Well, I know something about dx. It's related to du by this. So again, I got to get rid of dx. So if I solve for dx, my sentence would look like that then, wouldn't it? If I multiply both sides by 2. Agreed? And remember, we substituted that stuff right there for u. And so now the only thing we have to get rid of is dx. Well, what is dx equal to? 2 du. So if we put in 2 du, our integral would now look like that. True? And what could be done with that 2 right there? It's constant multiple, it can come out. So that means simplified version would be that. True? And now what do I notice here? That right there is a known derivative. True? And what derivative is it? It's that. So therefore we can go sine inverse of u plus c and be almost done. So, knowing that that's not one of the answers, because what did they do with the u? They did substitute back. What is u? What's that? And so if we look at our choices that we have there, does it match up with one of them? Should be letter A, huh? Alright. So again, in the scheme of things, it's not really any different than what we've done. We just have to account for the fact that there's chain rule issues sometimes when we have these functions. Okay? So again, this one's a little bit of a tricky problem because ultimately we have to recognize that we can put it in the right form by doing some algebra. Okay? Once we get it in the right form, though, we have a chain rule issue, so therefore we're going to use u substitution. Okay? And as I said, we're going to spend the next few days on working on substitution problems, so we'll get some experience making sure that we can know what to substitute using that du, getting everything to be x's out, u's in. Okay? And then once we do that, we can anti-differentiate and then plug the x's back in at the end. Okay? So that's the general strategy. We'll talk more about that tomorrow. But, okay. All right, probably have time for maybe one more, maybe two. Anybody else up through 14? Otherwise, we'll go on to 15 through 21. All right, we read the answers then. 15 through 21 are the following. 15 should be E. 16 should be E. 17 is C. 18 is D. Nope, I lied. It's C. Sorry. So 18 is C. 19 is B. 20 is E. And 21 is D. All right, how about from that group?
15.
And number 15 says, for what values is the graph of the function concave down? So we have 2 minus 4 over x, or 2 over 4 minus x, I should say. And again, it says, for what values of x is this concave down? So again, if this is our function, okay, what do we need to deal with if we're dealing with concavity? Second derivative. So let's figure out what is the first derivative here. Well, there's more than one way to do this. We could certainly use the quotient rule if we wanted to here. I personally would probably write it as 4 minus x to the negative 1 and use the power rule instead. Power rule and chain rule. Okay, if we do that, we're going to get the derivative here would be negative 2, 4 minus x to the negative 2 times negative 1. So the derivative inside is negative 1. And ultimately, those two would make 2 out in front. 4 minus x to the negative 2. So that would be my first derivative. My second derivative is going to be negative 4. 4 minus x to the negative 3 times negative 1. And so I'd have 4 minus x to the negative 3, which ultimately 4 minus x all cubed. So first step here is to figure out what is the second derivative. Okay. So if we use our differentiation techniques, we can find our second derivative. And ultimately the question is, for what values of x is this original function, is it concave down? So bottom line here is we need to know when is this right here, when is it less than 0 ultimately? Okay. So let's figure out, does it equal 0 ever? What do you say? Okay. Remember, keep in mind this is a fraction here. No way a fraction can equal 0 is at the top equals 0. So ultimately, again, can it equal 0? Okay. Now remember, inflection points can also occur where the derivative doesn't exist as well. So ultimately, what point would it not exist? 4. So 4 here would be a critical point for the second derivative, wouldn't it? So if we did our number line test with 4, if we put something to the left of 4 in here, what's our second derivative like? If I put something less than 4, like say 0 for instance, or 3 or whatever, it's going to be positive here, isn't it? And so therefore we're going to be positive here, which indicates that the function is concave up. And if we put something bigger than 4 in here, we're going to get something that is negative. And negative cubed is still negative, so we're going to get something negative here. So in fact, what do we find? That this is an inflection point, even though it doesn't equal 0, it doesn't exist there, so that is an inflection point. And we know that our function that is concave down in this area, which ultimately would be anything greater than 4. And so therefore we pick choice what? Choice C. Questions on that one? One more from that group? Mike? 19. And 19 says that we have an integral from 0 to 6 of x squared minus 2x plus 2 dx. And we're going to approximate that with 3 inscribed rectangles. And the key issue here is that word inscribed, because when you go draw the graph of this function, if we were to go from 0 to 6 here, we would have a 0 would give us 2, we'd be at 0, 2. And we're doing 3 rectangles, keep in mind, so I'm not going to put 1 in there, I'm going to put 2 and 4 and 6 to make our 3 rectangles. So 2 here would give us 4 minus 4 plus 2, we'd be back at 2. If you actually take the time to do the 1 here, you'd have essentially 1, so it'd be right here. And then ultimately here, when you get to 4, it's going to be up here somewhere, and 6 ultimately it's going to be way up here, so because we know it's a parabola. So ultimately we're looking at this kind of general shape. Now, in terms of inscribed rectangles here, if we were to go out at 6 and make a rectangle, then if we used RRAM, okay, for that one, we'd have to go back over the function, in which case it would not be inscribed, would it? Okay, so we wouldn't want to do that. The problem here, if we start at LRAM, if we did LRAM, we'd draw here, and that would also be not inscribed. True? And as a matter of fact, if you look at the 0 to 2 here, if I did RRAM, that would be inscribed, that would be circumscribed as well, wouldn't it? Both would be above the curve. So out of the 3 choices we have, LRAM or RRAM, those 2 are out. So what's the only other choice we have for this particular interval? MRAM. If we did the midpoint, wouldn't that be an inscribed rectangle right there? Alright, and then from here, what are we going to do for the rest of the interval? Well, wouldn't LRAM work for the rest? So remember, you can use any method you want to as long as they're inscribed. You want inscribed rectangles. That means that you have to use any combination of LRAM, MRAM, or RRAM that will give us inscribed rectangles. So from there, we just calculate. Of course, we find the heights of these, find all 3 rectangle areas, and add them all together. But again, ultimately, that's the picture that we would use. We couldn't use LRAM or RRAM on that region because it would be above the curve. So we'd have to use MRAM. Right? And keep in mind, if we used MRAM or RRAM on either of these 2, it'd be above the curve. So those would be no good in those 2 regions. Okay? And like I said, ultimately, just find those areas, calculate. Should end up with 26, according to what I got here.